Bismillahirrahmanirrahim. Assalamu alaikum. In the last lectures, we had started discussion about yet another type of power electronic converters, that is AC to DC type of power electronic converters, which are commonly termed to as rectifier circuits. Okay, so in this case, the source of voltage is commonly of AC type, and then on the output side, it is desired that we should be having DC type of voltage available. In the discussion, we had discussed that we can have two different categories, that is broadly speaking, of AC to DC converters. The first category is called uncontrolled rectifiers, and the second category of these type of converters is termed as controlled rectifiers. So in the case of uncontrolled, we had discussed that we are primarily using a diode as a switching device, while in the category of controlled rectifiers, we had discussed that we are using thyristor as the switching device or switching element. Okay. Then another type of classification of these type of converters or rectifiers can also be done, that which type of topology we are using. Okay, we can have either half wave type of converters, or we can have full wave type of converters. Okay. Then since in this case we are having AC voltage available on the input side, so other type of classification could be that whether we are using a single phase voltage source or we are using a three-phase voltage source. So these are the different ways according to which we can have classification of the AC-DC converters or rectifiers. Okay. In the last lectures, we had started discussion about the uncontrolled type of rectifiers, that is in which we are having a diode as a switching device, and we had started our discussion from the simple half wave rectifier. Okay, and we had also considered that we are having a single phase voltage as the source voltage. Okay, and then this knowledge can be extended, since this was the most basic. So it was good to have beginning from this one once we master the concept related to this one. So the same could equally be applied to other type of rectifiers, that whether we have for example a controlled single phase half wave rectifier, or we have for example a single phase full wave diode based rectifier or thyristor based rectifier, and so on, ultimately to three phase. So basically we can have any of subcategory. For example, we can have controlled or uncontrolled from over here. Okay, then we can have it as half wave or full wave, and then the source voltage can either be of single phase or of three phase type. Okay, so then furthermore, in the case of single phase half wave uncontrolled rectifier, what we had done, that we had discussed that based on the type of load that we are having, okay, we will be having different type of output waveforms available. Okay, so we had discussed about a very simple type of load, that is resistive load. Okay, in which we are having only R as a load. Then we had also discussed in the next lecture related to that one, that we are having a combination of resistive inductive load, RL type of load, and then in today's lecture we'll be continuing our discussion with another different type of load, which is commonly termed as RLE type of load. Basically E refers to a DC voltage source on the load side. Okay, so this is what we had started our discussion about diode rectifiers, in which we are having on the source side AC, and on the output side we are having uncontrolled DC. So this is a simple block diagram of a rectifier. This is basically an uncontrolled rectifier, in which we can see and that we are having an AC voltage source, then we are having a diode as a switching device. It has been shown in the form of a block. Okay, so it can be, for example, a simple diode as we had or have in the case of a half wave rectifier, or it can be a bridge arrangement, which we will commonly be using in the case of full wave rectifiers. And then we can also have different topologies for three-phase half wave and three-phase full wave rectifiers. In the last lecture we had did not discuss the use of a capacitor. Going ahead, we'll also discuss that why and how we can employ a capacitor to smooth out the output voltage ripple. So as I have just mentioned, that we can either have a pure resistive load as shown here in this figure, okay, a simple R type of load, or we can also have an RL type of load. Let us see what is the difference in waveforms. As we can see here, as we had discussed quite in detail in the last lecture, that in the case of a purely resistive load, this is the source voltage, we can see over here labeled as Vs, okay, and the voltage across the load, which has been termed as Vd. Okay, during the positive half cycle, the diode becomes forward biased. Okay, so it conducts effectively. In the ideal case, it behaves as a short circuit. So whatever is available on the source side is transferred to the load side. So that is why we can see that Vd is also the same as Vs in the case of first positive half cycle. Okay, up till this point. Also, we can see that the current waveform is exactly in phase with the source voltage, as well as, of course, the output voltage, which is the same, because we are not assuming any losses across the diode. Okay, so the current through this circuit remains the same, and the value of current depends on the ratio of voltage to resistance. So that is why if we are having any sufficient value resistor, so that means that the current will be, of course, lesser than the voltage. Okay, but the waveform is exactly in phase with the output voltage or even input voltage in this case. Okay, during the negative half cycle, we can see that now Vd and I are plotted here, means this line basically represents that we are having Vd and I both over here, because now the diode becomes reverse bias, because the polarity of the source voltage changes. Okay, so once it becomes reverse biased, it does not conduct, it behaves as an open circuit in ideal case. Okay, so because of that, we'll have no transfer of voltage to the load. Okay, and we'll have this output voltage labeled as Vd, as well as the current through this loop, okay, equal to 0, while the source voltage will stay as it has been. But now the voltage across the diode, which was previously 0, so it is good that during this discussion we'll also get a clear idea that how these labels have been assigned. Okay, these are normally plotted separately for each of the case in this book. The author has plotted them all together. Okay, so V diode in this positive half cycle is along this axis because it is 0, while in the negative half cycle, this is the waveform of V diode, okay, which is effectively the same as the source voltage, because all the potential appears across these two terminals of the diode. So that is how a resistive half wave rectifier with a resistive load behaves. While if we modify the circuit a little bit so that we are having some inductance as part of the load as well. So here the output waveforms across the load are of course different, okay, because not now this current will be not only offered some resistance by the resistive load, but it also will have to cope with this inductance. Okay, and the net voltage across the load has been labeled by the same variable Vd. Okay, so we can see over here that during the positive half cycle, of course the diode will soon become forward bias and it will start conduction, and the waveform of Vd will remain the same, okay, during this period, during this positive half cycle. Okay, but the waveform of current is not going to be in phase with the source voltage in this case, or the output voltage, either of them. Okay, the reason for that is quite obvious, that now we are having inductor as part of the load, and the current through inductor cannot change its value instantaneously. So that is why we can see that it takes the current to gradually increase from a low value, that is 0. It gradually rises to a maximum value. Until that point, the voltage across the inductor remains positive. Okay, and during this time we can see that this current and the voltage across the resistor, okay, if we take it separately, is in phase, okay, throughout this time duration. Okay, and we had discussed this quite in detail. Okay, that how the overall voltage across the inductor during this conduction interval uh, behaves, and it should be under the application of principle of inductor volt second balance. Okay, that the net sum of these voltages should be equal to 0. That is what we had discussed. So this keeps on conducting till all the current becomes 0, and then that is the point when the diode becomes reverse biased, and then that is the point when the source voltage appears across the diode. Okay, until then the diode keeps conducting. So now in today's lecture we'll be discussing the third category. That is the case when the load is under the influence of another component, that is DC voltage. So let us see that how does this behave. So if you draw the circuit diagram, the rest of the circuit will be same as we had last time. Okay, we are having a diode over here, then we can have some inductance as part of the load, and then we'll have a DC voltage. Okay, so the voltage across these three components combined is termed as the voltage across the load, while individually we can have like voltage across the inductor. Okay, and then we can have some voltage across the resistor as well, and of course we'll have voltage across the diode as well. Okay, so now let us see that how does this circuit behave differently as compared to the previous case that we had discussed, that is of okay, so this is the source voltage that we'll be having. Okay, now let us say that the voltage across this DC voltage, which is now also part of the load, it can be like we can take this one as, for example, a battery, okay, which is having some internal resistance, or any other component of similar nature which we are going to supply some power from this AC voltage source. Okay, so that is we can think of it as a practical circuit. That is how it is going to be. Okay, let us say that this is having some potential. Of course it will have if it is DC voltage source. Okay, and that potential is equal to, for example, a constant value. Okay, and let us say that value is somewhat in between the 0 and the maximum value of the AC voltage source. So this is the DC voltage of this this component, or this DC voltage which has been shown by ED. Okay, and this is our source voltage in black color. Okay, so now we can think of this circuit and its behavior, that how it is going to behave. Okay, now let us say that I want to plot the output voltage as we have been doing up till now, or you can say the voltage across the load or the voltage across the diode as well. Okay, so let us say that we are more interested in, for example, the voltage across the inductive part of the load. Okay, now in this particular case, in the previous case, what was happening, that when we had a simple RL type of load, that the output voltage or the diode started conduction immediately. Okay, this is not going to happen over here, because previously we did not have this component over here. Okay, and we could have, or we actually consider that this terminal of the diode is at zero potential. Okay, so as soon as the input voltage became slightly positive, the diode started conduction. Okay, but now here the case is different. In this particular case, or in this particular circuit, this terminal, the cathode terminal of the diode, is at this potential. Okay, so whatever is the peak value of this voltage source, okay, which I have shown over here by this color. Okay, so that is available at this terminal of the diode. So unless and until the input source voltage exceeds that value, it cannot cause the diode to become forward bias and start conduction. Okay, so in this case we can see over here the difference, that as long as the source voltage shown in black color over here is less than the DC voltage, this particular one, okay, which is also at the at which the negative terminal of diode is at the same potential, so it cannot cause conduction in this particular case. Okay, so up till now, up till this point, the diode will become, or will remain reverse biased. Okay, and it will not be able to conduct. Okay, but once we can see over here that the source voltage, which is available at the positive terminal of the diode, okay, exceeds the voltage at the negative terminal of the diode, so then it starts conduction. Okay, so this is the point when the diode will become forward bias and it will start conduction. Okay, but now here we have another problem. What is that other problem? The problem is that now what happens, that we have current over here. Okay, all right, we'll have output voltage from over here. Okay, you can see, but now we have this added problem, which we had from now onwards. The behavior of the circuit will be same as we had last time for for an RL type of load. Okay, so now what will happen, that if I draw the current waveform of this circuit over here, if we had only a resistive load, so immediately the current would have risen to that particular value according to the relationship between voltage and resistance. But now due to this inductance, the current will again gradually rise from like 0. Okay, it will gradually go to a maximum value, and as long as the source voltage is positive, okay, this device is conducting, it will keep on increasing. But as soon as the source voltage becomes lesser than the voltage of this battery or this DC voltage, so then what will happen, that it will try to cause the diode to become reverse biased. Okay, but now since we are having an inductor over here and it has been energized, it has gained some energy, and the inductor current, as we had discussed quite in detail in case of RL load, cannot immediately become 0. Okay, so what will happen, that I have not drawn the voltage waveform. Okay, so during this interval, the voltage across, so the time duration in which the inductor current is rising, okay, of course that is like the current through this whole loop, so that is why I'm labeling it as inductor current. Okay, as long as this current keeps on rising, okay, this is the current waveform, we'll have inductor voltage, okay, which will be positive. Okay, but as soon as it reaches its peak, okay, we had also discussed this previously in the case of DC-DC converters as well, that as long as it has a positive slope, okay, so the voltage across the inductor will be positive. Okay, at this peak, that rate of change changes to 0, and as we know from this relationship, that once we have this rate of change equal to 0, so that means the voltage across the inductor will also become 0. So that is the point at which the inductor voltage becomes 0. And after this point, now if we did not had this inductance over here, so that would have caused this diode to immediately become reverse biased and current would have become 0. But since we are having this energized inductor over here, okay, so it will not allow the current to become immediately 0. However, the current will start approaching 0, or it will have a falling slope from this point onwards up to a specific point. That depends on the actual value of the inductance. Okay, so from this point onwards, when this current is decreasing or it has a negative slope, so in that time duration this voltage across the inductor will be negative. Okay, and again, as we had discussed for RL type of load, that the principle of inductor volt second balance is still applicable, that the voltage in area A must be equal to the voltage across inductor in area B. Okay, so these will remain the same. Okay, so by the time that the inductor current, basically this time and this is the same. Okay, it's just because that this figure is not exactly according to the scale. We'll see the exact image or the exact figure in the textbook in a while. Okay, so these are different. Okay, so these are same as over here. This is the point in which it becomes 0, and this is T3. Okay, another book, it has been given the name as alpha. If we instead of T, we call this as omega T, and give it this axis the name of like in terms of its angles. Okay, so it can also be termed like this one. In different books, you will find different waveforms. Like in some cases, inductor current is becoming 0 within this interval. Okay, in some other cases, it might be the case as we had last time, that this may begin over here, and this will continue for a while, reach to another peak value. Okay, so basically that depends on that what is the relationship between the source voltage, okay, and this voltage across this particular DC voltage across the load. So this is the point till which the current will rise to a maximum value, and from that point onwards it will start to decrease, and that will of course depend on the value of the inductor, that up to how much it has been energized, and then how much time it requires to like allow that current to become 0. So it all depends on this relationship, the relationship of these two. Okay, one interesting equation that if you want to determine in terms of theoretical numbers, that what is the point at which this diode will become forward bias. Okay, so if we label this point or this angle as alpha, okay, that this is the starting point at which the source voltage will become more positive than the DC voltage across this source. Okay, so we can equate these two equations. This is the point basically at which these two are equal. Okay, so if Vs is equal to, for example, generally speaking, and omega T at this particular point is labeled as alpha, and at this point this is equal to this particular voltage. Okay, and if you want to determine the value of alpha, so this is how we can determine the value with the help of this equation, if you already know the actual numerical values of the source voltage and as well as the voltage across the DC source over here. Okay, now this is the circuit. It is much more clear over here now. Okay, as we can see in this figure, that we are having a diode, and then in the load we are having inductance. Resistance has not been shown over here, okay, but it can be or cannot be part of the circuit. However, the important point of discussion was this DC voltage source in the output. Okay, so just as we had discussed that this is our source voltage waveform, this is our DC voltage across the load. Okay, and as we can see over here that as long as this source voltage is less than this DC voltage, the straight lines of course shows the DC voltage, so the diode will not become forward bias and there will be no conduction. But once it crosses this line, this is that point which I described with the help of angle alpha. Okay, so in terms of time, in this book it has been labeled as T1. In the other book, that is of Daniel Hart, it has been labeled as alpha. So after this point the current will gradually rise. Okay, and till the time the source voltage is greater than the DC voltage, this one. Okay, so it will be conducting, and as soon as this becomes lesser than this, okay, so then the current will start to decrease. Okay, and during this time duration from T1 to T2 in which the current was rising, then had a positive slope, the voltage across inductor was positive as well, and then when the current had a negative slope, okay, it started to fall. Okay, so the inductor voltage also became negative. An interesting waveform for the voltage across diode, since up till this point, up till T1 or up till alpha, the diode was not conducting, so all the source voltage was appearing across the diode. There was no flow of current, as we can see over here. Then it became forward bias. Up till this point there was current flow. Okay, so the voltage across diode became zero or remained zero up till this point, and then after this point when the current became zero, okay, so that was the point when the diode became reverse biased, and whatever the source voltage, as we can see over here, that beyond this point all the voltage that was over there, but of course you'll have to subtract the voltage across this component from this waveform. Okay, and then the remaining one it appears across the diode, and then this process keeps on repeating itself. It is like worth mentioning to note that that the voltage across the diode, okay, is negative. That is because as we can see over here in this figure, that as I had mentioned in the beginning, that till the point when Vs is negative, then Ed, okay, so of course the diode will not be forward biased and it will not be conducting. Okay, but this voltage across the diode is negative because this is at higher potential as compared to this one. So if it is if we take the difference of these two, so we'll have a negative number in our response. We can gradually the source voltage approaches the Ed value, and at this point they became equal to each other. The difference becomes zero. Okay, and once this becomes higher than this one, so then of course the diode starts conduction.